Hello, Year 13. Welcome back to Chemistry, Term 2, this time online. I thought I'd start off with looking at a concept of electronegativity again. I remember we looked at that last year, Year 12, and we used electronegativity to explain why some covalent bonds were polar and some weren't. And then we used that idea of the polar bond within a molecule and the arrangement of those polar bonds to explain why some molecules were polar and some weren't. This year we want to look at the trends in electronegativity in the periodic table. Now, in this slide here, it shows a little graphic here, which I guess can help us to understand what electronegativity means when we're looking at a molecule. And that is two different atoms, different types of atoms tugging on the bonding electrons, and one of them will in a sense win more than the others, so will drag the electrons closer to its nucleus and therefore make the other atom in the bond slightly positive. So the one that wins will be negative, the one that loses will be slightly positive. You might recall last year we looked at why some bonds are polar and some are ionic and so forth. For instance, in the molecule of H2O, you have the HO bond, which is a covalent bond. It's a polar covalent bond because hydrogen and oxygen have different electronegativities. So polar means there's an uneven distribution of bonding electrons. There will be valence electrons involved with the bond. So you can imagine two atoms here, and the electrons involved with the bond are slightly closer to one than the other. And so we would say, well, in that case, the one that is losing would have a slightly positive charge on it, on that side of the bond, and the other one, the one that's winning, will have the slightly negative charge on it. And in some cases, when that is extreme, the difference in electronegativity is extreme between two atoms that are bonded, you actually get an ionic bond formed. In other words, one atom will actually capture the electron of the other one and become positive and negative, like these ones here. The sodium has lost an electron and the chloride has gained an electron. So that's the extreme case. Now, just recalling where this idea of electronegativity came from, Linus Pauling was the scientist who came up with a scale which was from 0 to 4. He based it on the size of the atoms involved and also their tendency to attract electrons, called electron affinity. And that's got something to do with how full the electron shell is, electron shell is. And we've already talked about atomic radius. Fluorine is the most electronegative element there is. It's quite a small atom, and it also is in group 17. So being small, its valence electrons are really close to its nucleus, so there's quite a big attraction there. And also the electron affinity will be great because it's in group 17. It has 7 valence electrons, and it would want to gain another one to form a full valence shell. A lot of the metals have a low electronegativity. That's why they tend to lose their valence electrons to form ions. So we have a scale here. We see fluorine up there with 4, electronegativity of 4, and the metals, as I say, are quite low. And in year 13, you should really know the order of the elements, at least these ones. So we start with the biggest one in the group 17 there, and then it goes fluorine, oxygen, chlorine, nitrogen, sulfur, carbon, hydrogen. Easy way to remember that is quite appropriate at the moment. Far out class, no school. about that. Now, looking at the periodic table, we find that electronegativity increases as you go from from group 1 up to group 17. Group 18 isn't included because it doesn't form bonds. Now remember, this trend is about atoms in a bonding situation. So across the period, there is an increase in nuclear charge. That means the number of protons in the nucleus, the atom. But the valence electrons remain in the same energy level. So that's important because the energy levels are like shells of an onion and increasing distances from the nucleus. So if they're in the same one, they're roughly in the same radius from the nucleus, distance from the nucleus. So there is an increase in attraction between the nucleus and the valence electrons, including those involved in bonding with other atoms. Now that's the crucial thing here when you're talking about electronegativity. So the attraction for bonding electrons increases across a period. Okay, going from 1 to 4 in this particular period, period 2. Going down a group, we see there's a trend as well. Fluorine is 4, chlorine's about 3.1, bromine's about 3. You'll see slight differences depending where you get the information from and how it's measured. So going down a group, how can we explain that? Well, we can say, well, the valence electrons, and therefore the bonding electrons, which are the valence, are further removed from the nucleus because their energy level increases. So the attraction between the nucleus and the bonding electrons, in other words, electronegativity, decreases going down a group. So when you find two atoms that are bonded that have a large difference in electronegativity, they will form ionic bonds. If the difference in electronegativity is smaller than is required to form an ionic bond, then the bond will be a polar covalent bond. A good example of that is the bond between hydrogen and chlorine. Now, chlorine is more electronegative than hydrogen, so that is the negative side of the bond, that is the positive side. Bonds between atoms of identical electronegativity, for example, in elements, molecules of elements, you'll find it's what's called a pure covalent bond. There's no difference. There's an even distribution of charge across those two atoms. So we talk about a continuum. That's the continuum idea, where depending on the difference of electronegativity, we go from pure covalent in elements to polar covalent to ionic. And when you're defining something as ionic, scientists talk about percentage ionic character of a bond. So in other words, it's not purely cut and dried, these distinctions. You might find there's some sort of level of covalency in the bond. In other words, the valence electrons might actually spend some time near the other ion. So that's just the idea that it's a sort of a range. Okay, some work for you to do. We have work from Education Perfect course, and then you'll find some exercises to do this week on this in your study guide. Hopefully you've got that at home, and this iPad. I'm pretty sure most of you will have that at home, thankfully. But if you haven't, just use one of the other resources and focus on that. So I've just set 2 questions from this one, and there's 3 pages from this iPad. Okay, all the best.